The objective of this video is to develop magnetic equivalent circuit fundamental components. We've previously introduced the magnetic equivalent circuit as an analytic tool to solve Maxwell's equations, specifically to solve for the magnetic field within a geometry. We're now going to formalize it. This tool fits neatly into our toolbox of approaches to solve Maxwell's equations within the cross-section of our machine. And as you'll see, to effectively use this tool, we need to have a solid understanding of the physics of our machine. We need to have foresight into the paths that our magnetic field is going to take. So we're going to start this by talking about flux tubes or reluctance elements. And I'll sketch a generic flux tube here, which has some length of L04 and has two surfaces, surface 1 and surface 2, which I've labeled, and I've put a dot in the center of these surfaces to indicate a node. This is like a node in an electric equivalent circuit. And as you recall, we developed magnetic equivalent circuits in analogy to electric equivalent circuits, and so we'll be continuing that analogy in today's video. And within this tube, we have field that is flowing. We've got magnetic field that's entering one surface and exiting another surface. And we've created our flux tube so that the following items are true. In fact, we've defined the flux tube to ensure that these will be true. We've defined it so that the H and B fields are perpendicular to the two surfaces. And when I say that we've defined it, it means that we've taken our cross-section of magnetic material and we've identified a path in that magnetic material that this will be true. And when we identify that path, then we can say that there's a flux tube here or there's a reluctance element here. And we'll talk more about identifying where flux tubes lie within a surface later. But let's just assume that we've identified that path right now. And what does it mean to have a flux tube? So H and B are perpendicular to surfaces 1 and 2. And we're also going to assume or define our flux tube so that H and B are uniform across each surface. So that means that the B field you have up here is the same as the B field you have down there. The whole surface is uniform. And another way of saying this is that these surfaces are equipotential. And this is again directly analogous to resistors in electric circuits. If you have a tube that represents your resistor, you assume that the electric field is uniform across the entire cross-section of the resistor. In classic circuit theory, you don't have any notion that you'd have a stronger current density here than you would over here. Rather, you assume that this whole surface has an equal current density, and we're making the same assumption for flux density. And then we also treat our permeability as being constant within the tube. And the total flux crossing through our first surface, which is equal to the integral of b1 dot ds1, is equal to the total flux crossing through our second surface, which is just equal to the flux passing through our tube. So what does this mean? This means that no flux leaves the sides. We do not have this. We have no flux leaving out here. All of the flux completely passes through the tube in the axial direction, entering surface 1 and leaving surface 2. So with these assumptions, or with this definition of our flux tube, let's now talk about reluctance again. And we define reluctance similar to resistance. So when we talk about resistance, electric resistance, we say that's equal to our voltage divided by our current, and voltage is equal to negative E dot dL from surface 1 to surface 2. So again, this quantity is voltage, or voltage from surface 1 to surface 2. So Ohm's law is that resistance is equal to voltage divided by our current. And in our case, we've defined reluctance so that reluctance is equal to a magnetic voltage, H dot dl, divided by the flux that passes through our flux tube. And this quantity, integral of H dot dl, when we talk about it from one surface to another surface, we call it a magnetic voltage. If we talk about it over a closed loop, we call it an MMF, and we'll clarify that a little bit later in the video. So this is magnetic voltage, and we can say that the following is true. It's equal to the potential at surface 1 minus the potential at surface 2. Or we can equivalently say that the integral of H dot dl is our voltage drop from surface 1 to surface 2. If we now rewrite reluctance in terms of our magnetic voltage, we can say that it is equal to the magnetic voltage on surface 1 minus the magnetic voltage on surface 2 divided by the total flux passing through our tube, which looks a lot like our resistance equation. And we can also sketch this in circuit form. We can talk about our reluctance element with a potential voltage on one side of UM1 and a potential voltage on the other side, a magnetic voltage, as UM2, connected to an MMF source, which is driving a flux. And so this is well and good. This is also a very simple example here that you have a single MMF source driving a flux through one reluctance. In actual useful examples, we're going to have a network of reluctances or a network of flux tubes and perhaps a network of MMF sources as well. And so then we'll be solving that equivalent circuit to determine our flux at all locations. And since B is assumed to be constant across the cross-section of our flux tube, we can turn our flux into a flux density at any location by dividing the flux tube flux by the cross-sectional area. What we do is that we formulate the circuit, and then we solve the circuit. So we figure out our MMFs, our magnetic voltages, and our fluxes. And then we can convert phi to flux density by saying that B is equal to a flux tube, flux, divided by the cross-sectional area of that flux tube, or the surface of the flux tube. Because remember that there are two surfaces. You have surface 1 and surface 2, and in general, they may actually have different cross-sectional areas. Okay. Let's take a step back now and talk about MMF, magnetic voltage, and current linkage. And so these are terms that you will see throughout your study of electric machine design. They can be somewhat ambiguous, so it is nice to have a clear definition before you immerse yourself in this world. So we've previously said that MMF is equal to the closed loop integral of H dot dl. This, using Ampere's law, is equal to the surface integral of J dot ds. As you'll find in your book, this quantity of J dot ds is equal to the current linkage. So we have the left side of our equation, which is described as MMF, and we have the right side of our equation, which is the current enclosed in our magnetic path, or our current linkage. Let's expand this a little bit. MMF can be written as a summation of magnetic voltages throughout a magnetic circuit. So we sketched a magnetic circuit up here that had a magnetic voltage, and so if you sum up all your magnetic voltages along a closed loop path, you get the total MMF that is applied to that path. This is directly analogous to electric circuits. Voltage, or electric potential difference, and EMF, so EMF is equal to the sum of all your voltage potential drops around your circuit. And we're doing the exact same thing when we construct our magnetic circuit. We have an MMF instead of an EMF, and the MMF drives a flux through a closed loop. And so the sum of the magnetic voltages is equal to the MMF that's applied to this loop. Current linkage is equal to MMF, but we distinguish it physically. So in math land, they're equal. There's an equal sign right here, right? We have an equal sign right here. But physically, we talk about current linkage as being the source term, as being the physical phenomenon that makes this happen. And so what you'll see is that you can talk about current linkage as being the sum of the currents that link a path. And in simple cases, later in the course, we may express this in terms of a winding factor multiplied by the number of turns of a coil that links a magnetic path. And so I'm introducing this terminology early on, and we'll formalize winding factors and current linkage more in our next unit later in the course. Okay, so that's MMF, magnetic voltage, and current linkage. Let's now go back to our flux tube and talk about a simple case. I'll call it a simple flux tube, where in addition to the other assumptions, we also assume that the flux tube has constant cross-sectional area throughout it. So surface 1 and surface 2 both have the same cross-sectional area. And in this case, we can relate our flux tube flux as being equal to B times A at any location, because there's only a single cross-section. There's only a single cross-sectional area A, and so throughout the flux tube, we can always find B by dividing phi by A. And we know that B is equal to mu times H, and we know that the integral of H dot dl is equal to H times the length of our flux tube. Because we have a constant cross-sectional area, that means that H is constant along our path, and so we can just simply evaluate the integral by pulling H out and multiplying by the length. And this is equal to our magnetic voltage across our flux tube. And so therefore, we can say that H within our flux tube is equal to our magnetic voltage divided by the length of our flux tube. And if we plug this back into phi, we get that our flux is the following expression. And if we go back to our definition of reluctance above, where reluctance is our magnetic voltage divided by our flux, we can make the following calculation. And here our magnetic voltages cancel. So we end up having reluctance equal to the length of our flux tube divided by the permeability of our flux tube times the cross-sectional area of our flux tube, which should be a familiar result to you from our previous video. Now let's go through a couple more definitions of terms as housekeeping items. So we've talked about reluctance. We can also talk about permeance. And permeance is equal to 1 over reluctance. And this is analogous to conductivity. We can define reluctivity as being 1 over our permeability, and this is analogous to conductivity. I apologize. This previous one was analogous to conductance, and reluctivity is analogous to conductivity. Okay, so that concludes this video. In summary, we've developed the fundamental components of magnetic equivalent circuits. We've focused on flux tubes or reluctance elements, and then we've developed the notion of MMF, magnetic voltage, and current linkage, and shown how this relates to an equivalent circuit, a magnetic equivalent circuit. And we've talked about how these flux tubes can be simplified by assuming a constant cross-sectional area, which then results in a calculation very similar to the resistance for a tube of conductive material. And finally, we've defined permeance and reluctivity.